Okay, so in the end of last lecture, at the beginning of last lecture, we developed the matrix equations for an isolated spring and then went forward to show that they were valid. And in that case, we have a single spring with stiffness K. We've got two local displacements, Q1 and Q2, and two local forces, F1 and F2. And we showed that the equations that govern this spring, or we can put the constitutive relationships in matrix form for this spring, we end up with a 2x2 stiffness matrix and 2x1 displacement vector, F1 and F2. So we're going to be getting used to writing this quite a bit. Okay, so I'm going to shut down things on my computer so this stops lagging so much. Don't know what's going on. Okay, so got rid of the lag, working now. Let's just say where we're up to. I just drew this, so we've got this working for a single spring, and we are going to get used to writing this matrix a lot. Okay, this k minus k matrix. So this is all well and good as long as we've got a single spring, and all we could do with this, we ended up just revealing the constitutive relationships again, and that the restraints had to be equal to the applied force. So we showed that, and that's good. It shows the method works, but it's not particularly useful yet. So we're going to extend this to the simplest level of complexity we can add to this is just to add another spring. So we will slightly increase the complexity of this problem by adding another spring. I'm going to have to restart my computer. Right, let's try the third installment in this lecture. These gaps probably don't make much of a difference in the lecture, but it's just for context, when it's lagging, it's really hard for me to like point over screen because I've got to look at myself the whole time, which is bad enough anyway. But it's very confusing. So where we are, we're going to slightly increase the complexity of this problem by adding just another spring to this. Okay, so we're going to make a two-spring system. We've got three nodes connected by two springs. And now we have to say this is lagging. Let me see if I can fix this. Okay, that seems to be better. Okay, so now we've got stiffness 1, K1, and stiffness 2, K2. So this is spring 1, this is spring 2. And we're going to number the nodes as well. We've got node 1, node 2, and node 3. These are going to be our global coordinates, or our global node numbers. Okay, so we've got associated with these, we've got displacements, Q1, Q2, and Q3, but because those are global, I give them an uppercase term. So Q1, Q2, and Q3, and then I've got associated forces that I can apply at each of these nodes as well. So uppercase F1 is the total force at node 1, F2 is the total force at node 2, and uppercase F3 is the total force at node 3. Okay, so for the system that we had previously, we had just a single spring and we had this sort of matrix here. Okay, so this was local Q1, local Q2, force 1, force 2 on this spring. Okay, so we had lower cases of these because this was just the local forces. Now that relationship still holds true for this spring here and this spring here separately, so we'll do that. Let's say for spring 1 we can write, I've got to write this slightly differently, let's just say we may write local KQ equals P for each of these. It's going to be KE lowercase QE is equal to PE for spring 1. So the stiffness matrix, K, K, minus K, minus K. But because it's spring 1, I have to say it's K1. Okay, because that is the stiffness which is just off of screen up here. The displacements here, well, I'm just going to copy down Q1 and Q2. Now it's lowercase, so that means it's the local Q1 and Q2. And I'm going to put a superscript 1 here. I'll talk more about that in a second. And then F1, 1, F2, 1 here. So if we were to just remember, that's our spring. This is K1, F1, F2, Q2, Q1. These are all local coordinates. And what this is saying, the Q1 that belongs to spring 1, the Q2 that belongs to spring 1. F1 belongs to spring 1, F2 belongs to spring 1, and so on. Now this doesn't necessarily mean node 2 in the global coordinate system. It does mean that for element 1, but for element 2 we'll just do the exact same thing. Let's write this down, or spring 2 rather. I would have K2, K2, minus K2, minus K2, but I'll write down Q1, Q2 belonging to element 2, or belonging to spring 2. I'll probably just keep saying element because it brings it, we're dealing with finite elements and it's just easier to say that. I've then got force 1 and force 2 that belongs to that side of the problem. So we've got two sets of matrix equations now. We now have two sets of matrix equations. So one set up here for element 2 and one set up here for element 1. And they describe, this is spring 1, this is spring 2. That's all these two things describe. So we've got the local coordinates for displacement and force in each of these. But we can look back at the problem and we can say, go back up here and say, okay, well, Q11 is also Q1 of element 1. In fact, let's write this on in a slightly different color. So it's Q1 of element 1, lowercase, is actually just this one up here. This one up here is Q2 of element 1, and also this is spring 2, and the first node it's connected to is Q2. So it's also Q1 of element 2. And then this one here is only displacement 2 of node 2. And we can make very similar arguments for those forces. So let's just write that down succinctly. So we've got two sets of matrix equations, but we should be able to see that there's a relationship that we can determine between those local displacements and forces and the global reference frame. And we're going to look at just, in this first instance, we're just going to look at the displacements because we can't quite yet come up with full expressions for the forces. So we'll say that Q11 simply Q1. My screen stopped moving. Let's try and figure that out. Having a lot of luck today with this. Okay, I'm not sure where that froze or why it froze. There we go. Okay, so let's just recap what I said. We can see there's an equivalence between the local displacements and forces, which is these lowercase ones, and the uppercase. And we're just going to do the displacements for the moment. Q11, which is local displacement 1 of node 1, is simply global displacement 1. Q21 is Q2. Q12 is also equal to Q2. And Q22 is equal to Q3. For the forces, we actually have to sum them together. So what we'll end up showing is that F2 is equal to F12 plus F21. And we're going to build that up in a second, and we'll show that in a moment. Okay, but we're just going to use these displacements in the first instance. So we can take these things we just developed and we can substitute the uppercase global coordinates into these matrix equations, which are up here. So we can rewrite the two sets of matrix equations in global coordinates. So we have K1, K1 minus K1 minus K1, Q1, Q2 is equal to F11, F21. So all we've done is taken the expressions of Q1 and Q2 and put them in here. Okay, this is for element 1. And we can do the same thing for element 2. The matrix is unchanged. We've got K2, K2, minus K2, minus K2. And it would have been Q21. Okay, Q21 is Q2. So Q2, and we would have had Q22, which becomes Q3, uppercase Q3. Okay, and again, the forces remain unchanged. Had to think there. So we've now got these expressions with the same, not quite the same displacements, but we've got Q2 is in both of them. We'd like to be able to somehow put these equations together in a form that enables us to describe the behavior of the system as a whole. So what we need to do is we need to put them into having the same vector of displacements here. So to be able to, or in order to, we need to expand the equations above. And I don't mean expand in the sense of mathematically expanding a set of brackets. I mean we literally need to make a vector of 2 by 1 into a vector of 3 by 1. And let's just say on this side, we've still got, this is our local stiffness matrix. Let's just check I'm using the same nomenclature as my notes here. Yeah, I am, that's good. Okay, so we've got, this is still local stiffness matrix, but we've now got uppercase Q global vector just for that element is equal to, nope, still lowercase. We're nearly there. We're almost there because we've got this just for this element displacement vector force for this part here. So in order to do that, I can see that, well, this one here is Q1 and Q2, doesn't have a Q3. This one here is Q2 and Q3, doesn't have a Q1. There's no reason why we can't just put them in there. So let's go through and do that. So let's do that operation. So this is going to become Q1, Q2, and Q3 is equal to F1, 1, F2, 1, and it's going to be nothing because we're just adding it. We haven't got anything to populate the right hand side with on here. And our previous 4 by 4 goes into the upper, previous 2 by 2 goes into the upper 2 by 2 here, and everything else is 0. So we have K1 minus K1, 0, minus K1, K1 and 0, 0, 0, 0. Okay, so this vector here is now the global displacement vector. Okay, this is still just for this element. Okay, and this is still just the element stiffness matrix, but it's a larger version of this. Okay, so we can say here, this is uppercase K, because it's in this global format, but it's still only for this element here. Okay, and if we wanted to, let's say we could do this. We could call this P, in this case, if we wanted. We're not going to use this nomenclature too much for this intermediate step anyway, but what we've got here, this is now in the global format. So if we had a much bigger problem with more nodes, this would be a mostly 0 matrix, okay, with just these 4 parts in there. Do the same thing with element 2. It's going to have the same displacement vector, so let's just copy this down. I can put the force vector on the right hand side. It's going to have a 0 at the top, F12, F22 rather, and then this is going to have 0, K2, minus K2, 0, minus K2, and K2, 0, 0, 0. Okay, so we've got the same thing here. Now this is still just element 1 and element 2, but these are now in the global coordinates. And what we can do, we can just add them together because we've got 2 sets of matrix equations. These are elementary row operations we can do. We can just add these 2 sets of equations together. We add every row in here and we get a new set of equations that describes the entire behavior of the system. So let's keep those up there. You can just about see them probably on screen. Let's add everything together. Well, we know what this vector is going to be. This is just going to be Q1, Q2, and Q3. This is our global displacement vector. It's probably easiest to add these up first. The non-conservative forces on the right-hand side. I've got F11, F22. This middle one is one where we've got two terms because we've got an entry in the middle row in both of these. So I just add them together. F21 plus F12. And then we do the same with the matrix. So I've got K1 here, minus K1, 0. I'm just taking the first row, it's only got items from element 1. Second row, I've got minus K1. And then in this middle one, I've got a K1 here and a K2. So I just add them together. And then in this part here, row 2, column 3, I've got minus K2. And hopefully the rest of this follows. So what we've got here, we should hopefully be able to see. Screen's not moving around for some reason. Screen dirty. Okay, so we've got this problem here. Let's just rewrite this right-hand side. Since this is the total forces on the nodes, we could rewrite this as F1, F2, and F3. And in fact, we could have done this earlier when I wrote down here F2 is equal to F12 plus F22. We could have done that. We could substitute on this right-hand side because we should be able to see here F2 is my global force here. I'm going to have acting, this would have been F21, sorry. Yeah, F21 and F12. Okay, so we add those two together, we get F2 here. But I just think it comes out a little bit easier when we just build these equations up together and you see them come out. Okay, so what we have here now is K, Q equals P for our problem. We've produced a set of equations for the combined two-spring problem that enables us to solve this problem, okay, if we have the boundary conditions. But let's just have a look at what we've produced. Well, let's look at a few things. We've got the stiffness matrix here is symmetric, okay, which means it's going to be singular, so we can't get the inverse of this matrix. And it's just really here, it's superposition of, if I was to colour this in, I hope that works. Yeah, that highlighting sort of works. Okay, so this one here is just K, E, 1. Okay, this is the stiffness matrix for that first element. And then if I look in the lower right hand side here, let's try a red underline. Red, yeah, that works. Okay, so this bit here is simply Ke2. Taking this stiffness matrix, put it in here, and we've taken this stiffness matrix and put it in here. And where they overlap, we've just added those terms up. Okay, so sometimes it helps to just think about what we're doing. We're taking this matrix, putting it into the right part of the system, putting it in here. Okay, maybe visually seeing this sometimes really helps with understanding how this problem is solved. Not so much how the problem is solved, how we construct this problem, let's say. I said we've solved it in the form that we wanted, which is good, which is the KQ equals P, but we still can't solve it yet. We can't solve it because there's still infinitely many solutions and we would have to restrain it somehow. So how do we solve it? Let's have a look. Well, we need a boundary condition, so let's say it's been built in at node 1. So node 1 is built in, therefore the displacement at node 1 has to be equal to 0. And let's produce some numbers for the stiffnesses. Let's say K1, just reading this from the notes, which I feel is fair because I wrote them. No, let's call them pascals, not kilopascals. K1 is 50 pascals. K2 is 75 pascals. And let's say that F2 is equal to F3 is equal to 7.5 newtons. Okay, so let's have a quick look at what this problem would actually look like. So we've got a built-in with a spring connected to another spring here. We've got two applied forces. We've got 7.5 newtons and 7.5 newtons, and we're looking for two displacements here, Q2, Q1, no, sorry, Q2 and Q3, and then the stiffnesses we would have K1 and K2. We've got the values for those, 50 and 75 pascals. We should be able to see that for horizontal equilibrium in this system, sum of forces in, let's call this the x direction, for the sum of forces in the x direction to be 0, we should be able to see there has to be a reaction here of 15 newtons. Okay, so before we go ahead and try and solve this as a system of matrix equations, this would be a handy check for us to be able to do, because when we solve this system, we're going to solve for displacements Q1 and Q2 and Q3 by, we're going to separate out those equations from KQ equals P. We're then going to be able to use those displacements to solve for this, and this should be 15, and if we've done that, then we know that our theory and our methodology is correct. Okay, I'm always trying to teach you guys little checks we can do to check we actually get the right answer. So our problem becomes, so substitution of these values into the problem. I've got a minor note as well. You guys are going to be annoyed at hearing how anally retentive I am. The phrase is substitution. If you're writing down English language to narrate one of your problems, you should say substitution. You shouldn't write plugging in. Okay, that's a colloquialism. So we say substitution of these values into our problem yields the following. So our matrix was K1 here. Now I can remember this off by heart. So it was K1 in this hand side, so it was 50. And then we're going to have minus 50. And then we're going to have 0. And then we're going to have minus 50. And then we're going to have 50 plus 75 in here, so we have 125. And then we're going to have minus 75 here, because that was minus K2. We're going to have 0, and then we're going to have another minus 75. And we're going to have 75 here. We've then got Q1, which is we've set to be equal to 0, so it's 0 here. Q2 and Q3 is equal to the unknown reaction, F1, and then we've got 7.5 and 7.5. So the bits that we don't know in this problem, Q1 and Q2. I can never remember which color highlighters work on this screen. I don't think many of them work particularly well. Okay, those are the bits that we don't know. They are F1, Q2 and Q3, and those are the bits that we want to solve. Gone out of focus. Let's see if I can fix that. It's not particularly important that I'm in focus, but let's see if we can fix it nonetheless. Oh, I'll come back. Perfect. Okay. So Q2 and Q3 are what we want to know. Those are going to be the displacements of nodes 2 and 3. So because we've got 0 here, we can disregard this first row completely. Sorry, first column completely. Unless you disregard this first row as well, and we can just look at this 2 by 2, this 2 by 1, and this 2 by 1 together. So enforcement of the boundary condition allows us to separate the part of the matrix corresponding to the displacements that actually are the unknowns. I've written that somewhat less eloquently there. We can then rewrite this as 125 minus 75 minus 75, 75, Q2 and Q3. Okay, and just a point to note earlier, this is symmetric, that's fine, but this isn't singular. Okay, it's the singularity of the matrix that makes it impossible to solve. Okay, so it's if it has a determinant that is 0. The big matrix up there would have had a determinant that was 0. This is symmetric, but we can actually work out this doesn't have a determinant that's 0, which is why we can solve for it. So we've now got this system of equations here. We can solve this to solve for the two unknowns. Q2, Q3 is equal to, now let's remember my matrix algebra. I need to swap these two and swap the sign of these. So that is going to be 75 in the upper left hand side, 125 in the lower right hand side. So 75, 125, 75 and 75 divided by 125 multiplied by 75 minus 75 squared multiplied by 7.5, 7.5. So let's get the trusty calculator out to work this out. One, 2, 5 times 75 minus 75 squared. It's 3,750. Okay, let's write this way. Let's do multiply by 75, 75, 75, 125. Okay, so let's do this now. 1 over 375. Well, this is a 2 by 2 matrix multiplied by a 2 by 1 vector. So we should expect to get two values out of this. So it's going to be 75 times 7.5 plus 75 times 7.5 in the top one, and then it's going to be 75 times 7.5 plus 125 times 7.5. 75 multiplied by 7.5 multiplied by 2, 75 multiplied by 7.5 plus 125 multiplied by 7.5. Now my 75 and my 7.5 times tables aren't particularly good, so let's put these together. 1125, and then I've got 75 times 7.5 plus 125 times 7.5 gives me 1500. Okay, and then if I do the division, Okay, so as long as the forces were in newtons and the stiffnesses are in pascals, so the answer we get out is in SI units, has to be in meters. So these are the displacements Q2 and Q3 of our problem. So we've got those out, and we can then go back to the equation that we got rid of. If we go all the way back up here, we can then determine the reaction. So now that we've determined we've determined the two displacements in the system, we can determine the remaining unknown, which was the reaction. So we go back up to this equation up here, and let's write this out. Let's see what F1, well, F1 was equal to 50 times nothing minus 50 multiplied by Q2. Okay. So let's put Q2 into here and we'll bring this down. Let's just copy this whole equation. I'm not going to copy it, I'm just going to bring this equation down. So this was the remaining equation that we had from the matrix. That's the sort of stuff that you should be writing down when I say it. Okay, this is the remaining equation. We can get the unknown from this. Q2 is 0.3, so F1 is equal to minus 50 multiplied by 0.3, which I'm pretty sure is going to be 15, equals minus 15 newtons. And that's what we said we needed to produce. Right back up here. Where was it? Nope, it was here. Here. We said the reaction had to be 15 newtons, and if it's going that way, it's in the opposite direction, so it's a negative number. So we've done a lot here, okay? This is starting to look more like a methodology we might be able to use to solve things. It's no longer, you know, we dealt with one spring, seemed a bit useless, but the instant we start adding these things together, so we had the single spring, put two of them together, we need to think about how we relate local and global things, and then we put them into these formats, which are just these local formats. We then said, okay, but these local bits correspond to some global numbers. So I can then put them with global numbers, I can make them bigger, expand them out, and then I'm going to add these bad boys together to get my global stiffness matrix, global displacements, global forces, and then I'm going to solve it. And in order to solve it, I need some sort of boundary condition. So I say it's fixed here, I know the force here, I know the force here, I don't know the displacement, don't know the displacement, and I don't know the force here. And we didn't cheat, but we said, well, we can see immediately what this force has to be. So this is a good check for us to go through. We picked the equations that we cared about, and that's sort of what boundary conditions are doing. Boundary conditions are making the problem solvable. And we're going to put the numbers in, inverted a 2 by 2 to solve this problem. That's easy for a 2 by 2 to do. It becomes much harder with, you know, even a 3 by 3 is pretty hard to do. So we can see this methodology is much more amenable to solving on a computer. We'll do maybe a 4 by 4 we might do by Gaussian elimination just to show you how we can do it. But we're going to have to start thinking about involving computers in this, and that's really why I started to put this up here, because this is quite a useful way to think about it. We can very readily construct a 2 by 2 for a spring. Okay, we're going to very readily be able to do that for a bar element. We just replace the K with EA on L. Okay, so in fact, you should be able to see that if we had for a truss structure, so if for a spring we've got KK minus K minus K, that's the stiffness matrix for a spring. For a bar element, we just end up with EA on L, 1, 1, minus 1, minus 1. So we could have done this whole problem that we just did for a truss that was like this. We could have done this as truss members with Young's modulus, cross-sectional area and length, and we could have worked out this, done the exact same thing and produced the exact same answer, as long as EA on L for each of those was equal to the two stiffnesses, which are 50 and 75 pascals. But hopefully this is starting to look like something that we can actually use. We're going to move on with this a little bit now. We've shown how important boundary conditions are for the problem. We can't solve this without the use of boundary conditions. So the ones that we've introduced so far are called homogeneous or homogeneous. I'm never certain how to pronounce that word, but they're homogeneous, whichever one it is, okay? What we mean by that is that we know the displacement is 0. So we can solve it for that case. There are other boundary conditions we can apply. We could have solved this problem by enforcing F1 is equal to 15 newtons, and that would be a non-homogeneous boundary condition. So we're going to go through and look at the different methodologies we can use to solve these. And then as we go through with this, we're going to start looking at bar elements, and then we're going to broach the bit that makes these all the more complicated, is that, you know, immediately even a structure like this, you can see if we have a structure with just 3 elements, if I pick this member out up here, then these two displacements, Q1 and Q2 for this element, they are not the same as either the horizontal or the vertical displacement of this node. So we need to produce something called a direction cosine matrix to be able to produce that, but it's actually pretty simple to do this stuff. Okay, so we're going to go through this, we'll finish it off. I'm going to do a couple more theory lectures before we start looking at coding stuff, but I would heavily advise you guys to start thinking about, can I solve this by hand? Maybe produce a Jupyter notebook to do the exact same method that we just did. And then we're going to start thinking about computational methods we can use to do the really difficult part of this problem, which is assembling the global stiffness matrix. Okay, so we've got to think about each 4x4 that we're going to be producing, because they will be 4x4 for bar elements. How do we fit those into different parts of a global matrix? Okay, so I hope this is fun. I really like this module. I think it's a really fun one to teach. I think it's a good, cool subject to get your head around. So I hope you're all enjoying your week. There's going to be some homework coming out soon for this week. There's going to be something on Blackboard. I've not decided what it's going to be yet, but it's just here to check that you're listening, following along, and understanding things. Okay, have a wonderful weekend, and I'll see you guys soon. Take care.